Hello, AP Calculus BC. This is Mr. Luya again. So I'm going to go ahead and in this video, I want to continue the notes for section 9.2b, and we're finding out the area of a polar region. So pretty much the first two examples of this section, we were kind of differentiating and finding rates of change or slopes of tangent lines with polar equations. Now what we're going to do is we're going to go ahead and kind of move into the integration aspect of polar equations. And what better way to talk about integration than area of a region? So I'm going to take a step back here. I mean, there's some good reading material here, but let me just kind of see if I can explain this in a little bit more simpler terms. But let's kind of take a trip back memory lane and sort of think about the XY plane, good old XY coordinate plane. If I wanted to say, okay, well, I want to find the area underneath this curve, and let's say from A to B, right? So this region is pretty much what I'm interested in finding the area of. What I'm essentially going to be doing, and the whole point of what we learned in calculus, is that we're essentially trying to find like a bunch of infinitely many small rectangles underneath this curve, figure out the area of all of those infinitely small rectangles underneath the curve, and then add them together. And there's a big, let me kind of pull out one of these rectangles out here. And the way that you can make these rectangles infinitely small is obviously the height's going to be dependent on whatever f of x is. So that's f of x right there. And then the width of each of those rectangles is going to be, we call it dx, right? It's not really an x value, but we're called to make it infinitesimally small. It's going to be d. I don't even know if I'm saying that word right. Infinitesimally. I don't care anymore. So anyways, yeah, that's what we're essentially doing. And what we're doing is we're taking the integral between those two bounds a and b, and then adding up all together. And really the integration symbol is kind of a derivation of a summation symbol. I'm not going to get into that formula in this class, but maybe in the future if you want to be math majors. But essentially we're taking the sum of all of the infinitesimally small rectangles of f of x times dx, right? Because that's how you find the area of a rectangle, one length times the width. And that's how you come up with that. So that's when we think about our good old XY coordinate plane. Now, when we're thinking about instead of a polar coordinate plane, well, we're dealing with theta now, right? And let's say I wanted to figure out, and I promise you, I hope you didn't skip the last video because this is going to be very helpful, especially that very last example that we did in the 9.2a notes. But let's say I have like maybe just kind of a curve like this, right? I don't know, I'll just give you the incomplete version of that curve. And let's say instead I want to figure out what is the area between an alpha and a beta angle. Okay? Because remember, whenever you're trying to graph in a coordinate plane, you're no longer going along like an x-axis anymore. Instead, you're going along a different thetas that are kind of going in this direction. So so really my upper and lower bound are going to be angles instead. So that'll kind of get us started with how we're integrating the area of a polar region. So it's going to be between alpha and beta now. Okay, so now what we got to think about is what infinitesimally small area figures are we adding up in a polar region? So the thing is, we're not going to be creating little rectangles anymore. Instead, what we're going to be doing to find the area of this region right there, we're going to be going ahead and creating a bunch of infinitely small sectors of a circle. So let me see if I can draw that here separately. So let's kind of remember what a sector of a circle is. So a sector of a circle is something like that. Okay, it'll have a radius. This will have some kind of angle measure, right? Angle measure in our case, it's going to be in radians. So then if we think about how do we find the area of a circle, well, the area of a circle is going to be pi r squared. But a sector is pretty much a fraction of that entire circle. And that fraction is going to be whatever x is, right? Divided by the measure of the whole circle, which in radians we know is 2 pi. Okay, so kind of like what we said over here earlier where we said, okay, well, an infinitesimally small width is going to be dx. Let's instead think about what is an infinitesimally small angle measure, x. So what we'll do is we'll call this instead of dx, we'll call it d theta. That's an infinitesimally small angle measure. So let's replace that instead with d theta over 2 pi, and then pi r squared, right? So that's actually what we're going to go ahead and put the sum of all of these infinitely small sectors in that region between alpha and beta. So it's going to be d theta over 2 pi times pi r squared. And we can actually clean this up a little bit. So I'm going to cancel out my thetas. I can take out a 1/2 outside. So it'll be 1/2 the integral from alpha to beta. And then it's going to be r squared. Now, if you remember from before with the notes, you know that r is always going to be some kind of function with a variable theta. So we can actually replace r squared with f of theta squared. And then the d theta we'll just put there. So some function of theta squared, which is usually going to be whatever r is, right? Function of theta squared d theta from alpha to beta times 1/2. And that's how they came up with that area. All right, so you're going to find out that the setup of all of these areas for polar regions is extremely easy until you get to deciding what your alpha and beta are. That, in my opinion, is the hardest part about this whole section. I remember I struggled with it when I took Calculus 3, and I know you guys will too. But again, before deciding what alpha and beta are is going to be extremely helpful if you actually go back to I don't know if I even have it on my nearby. I know I went over it, but if you go back and look over those notes where we actually graphed the rose petals, right? The last example of 9-2A, go back and rewatch that, because that's going to help you understand kind of like how to decide what angles to pick from if you know how it's drawn. So let's just kind of get into it. Get some extra paper here for some cushion. So, all right, let's look at this first example. So example number 3, it says find the area of one petal of the rose curve given by r is equal to 3 cosine of 3 theta. Well, if that looks familiar, it's probably because we've already graphed this at the end of the notes that I told you to go back and check. So here's what we're going to do. But here's the thing. They're only interested in one petal of that rose. So let's think about this. If I think about how I'm going to start, now granted, a lot of times they're not even going to give you the graph. This would be a pretty good multiple choice question, but they're not even going to give you the graph. So you're going to have to kind of like decide for yourself how you're going to graph this. So I don't know if you remember, but like if we were to graph this and we had theta and radius, right? We know that at theta of 0, it was going to be 3 cosine of 0, which was 3. So that's kind of like where we started off with our rose petal, right? And so now let's see. I remember that from here, we're going to go and we're going to get to the next point of our petal, we kind of just, went up here, and then eventually we came back to that right there. Okay, so let me just kind of give you like a heads up. So we went that way, and then we got that rose petal right there. I'll tell you right now, this is actually going to be all we would need in order to answer this question, right? Because if you think about like what like the rose petals from back in the day, and I mean, I hope my explanations are pretty clear here, but if you think about the rose petals, like weren't they kind of like all symmetric when you kind of created the rose petal? Like this area of the rose petal was symmetric with that one down there. So if you think about it, when we set up our integral, right, we can go ahead and figure out what the area is for just half of this rose petal, and then multiply it by 2 because we know it's going to be symmetrical. And you're going to find out that that's what you're going to be doing with a lot of these problems. So let's figure out, okay, so from what theta to what theta, so we know from a theta of 0, right? So let me set up the integral. So we have the integral 1/2. We know that our function is going to be 3 cosine of 3 theta. and then all of this squared, and then d theta. All right, so we're already like, we already took care of a big part of the battle, but the bigger part of the battle is actually what the bounds are. So here's the thing. So if I create my rose petal, right, I know that from 0, that's kind of where it started. That's going to be like our first angle. If we can figure out what angle brings that rose petal back to the center, right, then so at what angle will you have a radius of 0 there? Okay, then you're going to know, well, that'll be my alpha, that'll be my beta, and then that'll give me the area of half of a rose petal. And then what I can eventually do is just get this whole result and just multiply it by 2. Okay, so let's kind of go ahead and figure out what angle is going to bring your radius back down to 0. So if we plug in 0 in for radius, that's going to be 0 is equal to 3 cosine of 3 theta. And so that means that cosine of 3 theta is going to be equal to 0. So now we have to think about, okay, well, what angles actually give us cosine of what angle gives us 0? And so we know that that's going to be pi over 2, 3 pi over 2, so on and so forth. But remember, it's the cosine of some angle gives us 0, but this angle is actually 3 theta, right? So we need to figure out, okay, well, what theta is going to cause all of, so we can divide everything by 1/3. So we know that theta is actually equal to pi over 6, pi over 2, so on and so forth. So I don't know if you remember way back when we did the notes. I wish I had them nearby just so that I can show you again, but I do not. Whatever. All right. So you know that if you plugged in pi over 6, like if you continued and you started at 0 and you kept going until you get to pi over 6, then that'll bring you back down to the that radius of 0 for that rose petal. So we know that from 0 to pi over 6, we know that this expression right there is going to give us the area of half of a rose petal. Right? And because we know that this is symmetric with like the other half right there, all we'd have to do is multiply it by 2, and that gives us our final answer. So let me just clean this up a little bit. So I know that the area of one petal is going to be equal to the integral from 0 to pi over 6 of, because 2 times 1/2 will just cancel out. And then it'll pretty much be 3 cosine of 3 theta squared d theta. Okay, and if I put that in my calculator, which is nowhere to be found, oh, here we go. That's very convenient. So if I plug that in my calculator, I'm going to do math 9 from 0 to pi divided by 6 of 3 cosine of 3x x. That was not the answer I got earlier. Am I in the right mode? Oh, I forgot to square it. Insert parentheses, square. Did I put an extra parentheses that I didn't need? That's not it either. What the heck? Is it recognizing the 3x as being squared? Let me put an extra set of parentheses. Oh, I think it's only squaring the cosine of 3x, so 3 cosine of 3x, parentheses, all of that squared. That should give us, there we go, the right answer, 2.356. It's equal to 2.356. So be careful here. Make sure that it's squaring the whole thing, because I mean with this one it was only squaring the cosine of 3x and leaving the 3 as 3 when it's actually 9. In fact, I wonder if if I would have changed this to 9, then it would have given me the same thing. Yeah. Okay. So that's equal to 2.356. Now, I mean, granted, I don't know if a calculator would be allowed for all of these. I'm just using the calculator just to kind of, because really the whole point of this lesson is to help you with the integration setup. But sometimes you will be required to go ahead and change this yourself and integrate this using integration techniques that you know. And right off the bat, I already know that, you know, if you don't remember how to integrate something like this, then you probably need to revisit chapter 6 or some of those worksheets that we've done in the past. Because I know that what we would end up doing is we would end up doing like using that one identity where cosine squared of x is equal to 1 plus cosine of 2x over 2, right? So in this case, that means that the cosine squared of 3 theta is the same thing as 1 plus cosine of 6 theta divided by 2. Yeah, that's a theta. Of 6 theta divided by 2, and then you can replace that with that, and then, yeah, you can just go ahead and integrate using maybe u sub or integration of cosine. But I'm not going to get into that right now. How long is this video already? 16 minutes. So I want to make sure that I get through another example because I don't want to make these videos too long. But keep in mind that you will have to probably integrate this by hand. Okay? And that would at least get you started on how to do that. So if I look at example 4, this is my least favorite video so far. But anyways, if I look at example 4, it says finding the area bounded by a single curve. So I don't know why I said use your TI Inspire. I obviously took this problem from another teacher, but it says find the area of the region lying between the inner and outer loops of the limacone. I think that's how you pronounce it. The limacone r equals 1 minus 2 sine of theta. That's it. I don't really even need the rest of these directions because we're going to do this without the TI Inspire. So, okay, they want to know what is now, crap, this didn't print out nicely, but I don't remember if I printed it out nicely on your notes, but essentially there is an area of a region like this, right? This is the area that they're trying to find. My notes didn't print out that nicely. So essentially what we want to know, if we want to figure out what is the area of the shaded region here, that's going to be equal to the area of the outer shell or the outer loop. You know, let me say, or really I'm just going to say the overall loop, right? Because really it's the overall area of all of this minus the area of that inner loop. Because the thing is, if I find the area of the outer loop, the whole outer loop, it's going to include that like enclosed region there. So at the end, I'm going to have to subtract that area of the enclosed region there. So I don't know if it's going to, whatever. So if I find the area of the outer loop or the overall region, it's going to have that. So then what we're doing is we're subtracting the area of that inner loop. So minus the area of the inner loop. Okay. So this isn't so bad. So why don't we, let me go ahead and do this. Let me figure out what the area of that inner loop is first. So area of the inner loop. And the way that the setup is pretty simple. It's going to be 1/2 integral of whatever our function is, 1 minus 2 sine theta d theta, all of this squared. But the thing is, the bounds is what's really going to make this difficult. So let's just kind of think for a second here. What happens if I were to put theta and r, right? Let's say I started with 0. Now, granted, I did kind of give it away here, but let's pretend that those were not given to us. In fact, a lot of times they wouldn't be given to us. I don't know why this teacher put the angles there. But if we think about like a theta of 0, if I plugged in 0 into my function, I'm going to have 1 minus 2 sine of 0, right? And what that's going to equal is 1. So really, the first point of this limacone, the way that they started to graph this, was it started off over here, right? At a value of a radius of 1. That is not the beginning of my inner loop. Because again, when I'm integrating from a lower bound to an upper bound, it has to start from here and kind of go loop around and go right back there to there. Okay? So 0 starts you off over here. So if you were to go ahead and put 0 as your lower bound, you're going to be including like this extra little area there that is not going to be a part of our inner loop. So we got to keep thinking about, okay, we got to keep going to which theta will get us to the beginning of that inner loop. And if you notice, the beginning of that inner loop does have a radius of 0, okay? So what angle value will give us a radius of 0? And that's what we're going to do. We're going to set this function equal to 0. So 0 is equal to 1 minus 2 sine of theta, okay? So if I work this around, I know that sine of theta has to equal to 1/2. Okay, well, if I went ahead and I figured out what theta is, so sine of what angles give you 1/2? Well, I know pi over 6 does, and I know 5 pi over 6 does, right? And so I'm pretty sure that if we go from 0, it's eventually going to like lead into pi over 6 first, and then maybe loop around, and then when we get to 5 pi over 6, it'll come back to 0. And that's kind of how, I mean, sure, if you want, maybe one day we can sit down and show you how the graph starts, but I'm pretty sure that the inner loop is going to get started with pi over 6, because that'll give us a radius of 0, and then that'll be our lower bound. And then it's going to start at pi over 6, and then we're going to keep putting in angles, and then it's going to like draw this loop around, and then by the time we get to 5 pi over 6, it'll finish that loop. Okay, so that's going to be 5 pi over 6 as my upper bound. So that was the inner loop, which was pretty nice, right? So now let's figure out what the outer loop is, or what the overall. I should have just put overall. I don't like putting the word outer, right? So the outer loop is going to be, well, 1/2 times the integral, same function, 1 minus 2 sine theta, all of that squared, d theta. Okay, so let's think about how this is drawn. So we started here, we went here, we got to our inner loop, then we went around our inner loop, and then like really at 5 pi over 6, that's when the outer region is starting to be drawn. So that's actually going to be our starting point right there, 5 pi over 6. And now we got to think about, okay, well, how do we go all the way around, right, to there? So if you think about it, we're gonna go. We're gonna start at 5 pi over 6, and then we're gonna keep plugging in thetas, and then it's gonna keep drawing the rest of this for us. And then we're gonna, once we get to 2 pi, right? It's gonna bring us back to sine of 2 pi is gonna equal 1. So it's gonna bring us right there. So really, that's not gonna give us all of the area that we're looking for. The completion of the outer loop is gonna go just a little bit further out into yet another pi over 6. So not just 2 pi, but 2 pi plus an extra little pi over 6 will get us back to the end of that outer loop. So this is going to end up being 12 pi over 6, so 13 pi over 6. So that right there is our upper bound. And that's going to give us the area of the overall region. So, all right. I mean, we did it. So it'll be area of the shaded region is going to be this whole thing, 1/2 integral from pi over 6 to 5 pi over 6 of 1 minus 2 sine theta squared d theta minus, no, I meant to say 5 pi over 6 and 13 pi over 6. So that it's the outer loop minus the inner loop. Minus the integral, 1/2 the integral. This is turning awful, but I think you guys got it. I hope. If not, I'll just tell me and I'll record the video. All right. There you go. So then you pretty much work that out. Okay. So I'm going to go ahead and just leave it at that. And then I'm going to, let's see. And I did work out this problem already. Well, I have the teacher solution. So it's just going to be pi plus 3 radical 3. But this setup, if you just plug that in your calculator, you would get the right answer. Or if you actually took the time to work out all of these things. This is one where if you worked out the sine squared of theta, it's pretty much the same thing as 1 minus cosine of 2 theta over 2. if you wanted to work this out by hand, which you might have to. So I'll leave it at that. All right, so this definitely takes the cake of the worst video I've created so far this spring break, but that's okay. I think it made sense. I hope it did. If it didn't, let me know. Give me some feedback. I'm still new at teaching calculus, so keep that in mind and don't hate me. All right, but I do love you guys. Take care. Have a good break.